All right, in this video, we are going to move into section 3.6, which is titled Marginals. Not really anything like new-wise to learn. It's just going to be a different interpretation of what derivatives also mean in the business world. So have a few notes to go over the first couple slides, and then we'll work some problems. So in this section, we want to look at how to use calculus to make approximations. So this is kind of an example I want to read through really quick to kind of talk about how this works. And kind of show you in the real world where this may be useful. So let's suppose that an animal rescue organization is considering increasing its monthly production of public service announcements, which I'm going to call PSAs, from 12 to 13. To estimate the resulting increase in cost, it would be reasonable to find the rate at which cost is increasing when 12 PSAs are produced, and then add to that the cost of producing 12 PSAs. So what that means formula-wise is that we could find the cost of 13 PSAs by taking the cost of 12 and adding the instantaneous rate of change at the 12th unit. This number that we're calling C prime of 12 is the whole idea of this section. This is called the marginal cost at 12 units. So like I called it instantaneous rate of change a minute ago. Remember that C prime of 12 is also the slope of the tangent line at that point. Since the company has probably never produced 13 PSAs in a month, the actual cost C of 13 is unknown. While this will probably not give the exact cost of producing 13 PSAs, it would give you a reasonable estimation for C of 13 to make the best decision for your company. So we're trying to talk a little bit more about what this marginal cost idea is. Now, marginals, or generalizing this, marginals can be done for any of the three business formulas we've talked about. So we've spent a lot of time talking about cost, revenue, and profit. So let's assume that you have a total cost, a total revenue, and a total profit function. Well, all these formulas are going to look the same, so I'm only going to go over one of them and then kind of paraphrase through the other two. So let's talk about marginal cost. Marginal cost is defined as the formula C prime of X, and what this is that this is the approximate cost of the X plus first item. Remember in the example I just gave you, when they did C prime of 12, you were approximating the cost of the 13th item. You don't actually know what it is, you're just approximating. So what that tells us, and you can use this formula if you'd like, I don't really use it, but it says that C prime of X is approximately C of X plus 1 minus C of X, or moving things around, we can say that C of X plus 1 is C of X plus C prime of X. Now, mirror image here, this same idea can be applied to marginal revenue, and it can be applied to the idea of marginal profit. The one thing I want you to note is that when you find marginal revenue, you are approximating the revenue from the X plus first item, and then for marginal profit, you are approximating the profit of the X plus first item. So in layman's terms, what this slide is telling us is when you take the derivative of a function, either cost, revenue, or profit, and you plug a number into it, you are approximating the next item in line of the number you plugged in. So if you plug in 12, you're approximating 13. If you plug in 50, you're approximating 51. That's the idea of what marginals are. So outside of that, the rest of today is going to be all about working problems. So I've got a few problems I want to run through. A lot of them have multi-parts, and then we'll wrap up this video. So for example, number 1, if I tell you that the revenue function is 5x and the cost function is 0.001x squared plus 1.2x plus 60. First off, I want you to find the total profit function. So we've done this in the last video a bunch, but it doesn't hurt to review it. Profit is found by taking the revenue function and subtracting the cost function. So this would end up being 5x minus the cost function, which is 0.001x squared plus 1.2x plus 60. If I distribute that negative through, it is 5x minus 0.001x squared minus 1.2x minus 60, which, putting my terms together, this is negative 0.001x squared. 5 and let's see, that's positive 3.8x, and then minus 60. This is our profit function. So part B has nothing to do with calculus, just kind of practicing with your calculator here a little bit. I want you to take the number 100 and I want you to plug it into the revenue, the cost, and the profit function. So here we go. R of 100 is going to equal 5 times 100, which gives you a revenue of $500. Your cost function of 100, so plug 100 into the original cost function, would be 0.001 times 100 squared plus 1.2 times 100 plus 60, and getting my calculator out. Let's see. That would give me a cost of $190. And then where you can be very sneaky and very clever about this is that if you want to plug 100 into the profit function, that is fine. Or you can think realistically. If you bring in $500 of revenue and it costs you $190 to make it, then by doing basic subtraction, we could say that our profit has to be $310 just by the knowledge of what profit is. But if you don't believe me or you don't understand that idea, you can always plug 100 into the profit function in blue up here, and you should get $310. All right, so for part C, we want to find the derivative of all three functions. So what I'm going to do up here at the top is I need to write all three of them down. So I remember 5x, and let's see, cost is going to be, let me backtrack really quick. Cost is 0.001x squared, so 0.00. It was plus 1.2x, and I apologize, plus 60. And then your profit function was negative 0.001x squared plus 3.8x minus 60, I believe. Let me make sure. Yep, there we go. All right, so part C. Find the derivative of all three of those functions. So r prime of x is going to be 5. That was pretty simple. C prime of x is going to equal, let's see, 0.002x plus 1.2. And then the derivative of your profit function is negative 0.002x plus 3.8. And now here's the idea of this section. I now want you to take these three derivative functions and let's plug 100 into all of them. So first off, r prime of 100, there are no x's to plug in, so therefore not much you can really do there. Your answer is $5. And remember, derivatives are rates of change, so these numbers should be a lot smaller here. C prime of 100 is going to be 0.002 times 100 plus 1.2. Just double checking that. I think I know what it is, but I don't want to mess up. That should be $1.40. And using the same realistic idea, if you want to plug 100 into the derivative of your profit function, you can. I'll do it this time. So it's negative 0.002 times 100 plus 3.8. But that should come out to be $3.60, which some of y'all might notice is the same thing as $5 minus the $1.40. So here's the purpose of this section. What are these three numbers that we just found in part D? Explain what each quantity represents. So what this is the approximate, and that's the key word. This is the approximate revenue, cost, and profit of producing and selling Now remember, this approximates the next item of selling the 101st item. So all three of those numbers, what this says that if we're approximating that, if we were to go to the 101st item, we would bring in $5 of revenue. It would cost probably an additional $1.40, but you would bring in an approximate profit extra of $3.60. And that gives you an idea of what to expect as you move through. Is it worth trying to go to the next item based on these approximation values? All right, let's do another one. Like I said, a lot of multi-part questions in this section. Number 2, suppose the daily cost in hundreds of dollars of producing X security systems is C of X equals 0.002X cubed plus 0.1X squared plus 42X plus 300. And currently you produce daily 40 security systems. So part A is a very simple question, nothing to do with derivatives. What is the current daily cost? So all I'm going to do is take the 40 that you currently produce and I'm going to plug those in. So C of 40 would be 0.002 times 40 cubed plus 0.1 times 40 squared plus 42 times 40 plus 300. And let me type all this in my calculator. I cannot do that in my head. So you get 2,268. Now, this is the cost, but it says this is the cost in hundreds of dollars. All right. So you're going to have to remember that this is represented as hundreds of dollars. So to get the actual cost, you will have to take 2268 times 100. So times 100. That would give us a cost of actually $226,800. Once again, I multiplied by 100 here because that would be, because it says the supposed daily cost in hundreds of dollars. This is what's telling us to do that. So part B says, what is the marginal cost when X is 40? Well, for this class, when you see the word marginal, that means take the derivative of that function. So I need to find C prime of X. So if I take my first derivative, that would be 0.006X squared plus 0.2X plus 42. And then I want to plug 40 into this derivative. So C prime of 40 would be 0.006 times 40 squared plus 0.2 times 40 plus 42. Let me type all this in again. 40 squared. Oops, wrong button. Hang on, plus 0.2 times 40 plus 42. This gives me 59.6. But remember, these cost functions are in hundreds of dollars. So 59.6 times 100 would give me a marginal cost of $5,960. So remember, while it's not asking for this, remember what this number is. This is the approximate cost of producing the next item in line, which would be 41 security systems. All right, part C and part D. Part C says use the result from part B to estimate the daily cost of increasing production to 42 security systems. All right. So we are trying to estimate here. So I'm not trying to find the actual cost. All this wants you to do is it wants you to take the current cost of selling 40. So that is the $226,800. So we're going to take $226,800 That's how much I know it costs to make 40. I want you to use the number from part B, and the number from part B was 5960. So we're going to add $5,960. That would give us a 41st security system. We're going to assume this trend continues. So to get to a 42nd security system, I'm going to add 5960 again. And if I add these up, this gives me an estimate cost of making 42 security systems to be $238,720. Is that the exact cost? Probably not, but we're using our marginal value from part B to get an approximate number that it might be. So now the question becomes, so what would be the actual additional daily cost of increasing production to 42 security systems? So in this case, I want to know actually what is C of 42. So I want to go back to my cost function, and I just want to plug 42 in. So let's see how close we are. So a little writing here, that's going to be 0.002 times 42 cubed. Hopefully you have this in front of you while I do this. Plus 0.1 times 42 squared plus 42 times 42, and I believe it was plus 300. Yep. So if I type this into my calculator, let me see if I can kind of cheat here a little bit. Yeah, we'll take this one. We're going to change all of these. Oops, no, we'll just start from scratch. I messed up. Sorry. So 0.002 times 42 raised to the third plus 0.1 times 42 squared plus 42 times 42 plus 300. This gives me an answer of 2388.576. But remember, this is in thousands of dollars, so you have to multiply it by 1,000. And this gives me 200. Yeah, so 238,857. Oh, hundreds of dollars. Sorry, not thousands of dollars. Hundreds of dollars. So I was wondering why the number was so big. Times 100. So that'd be $238,857.60. So as you can see, these numbers are very, very close. Our estimate's off by about $137, but that's really not bad when the numbers are this large. Now, if it's actually asking you for the difference here, you would have to subtract this number minus the 226. I think it may make you break this down. So if you subtract off the original cost, so let's see, 238,857.60 minus the 226,800. The actual cost increase would be $12,057.60. So that's the actual increase for making the two. I'm not sure if it will ask for that number. It may just ask for this number. Just make sure you read your instructions and see which number it actually is. All right, number 3, another multi-part question. The supply S of a new rollerball pin is given by S equals 0.007 P cubed minus 0.5 P squared plus 150 P, where P is just the price in dollars. Part A says, find the rate of change of quantity with respect to price. So they want us to take the derivative of our S equation in terms of P. That's easy enough. So ds dp would just be take the derivative. So 3 times that decimal is 0.021 p squared minus, that just becomes minus p because that becomes 1, and then plus 150. This is our rate of change. Part B says, how many units will producers want to supply when the price is $25? Now, it doesn't mention anything here about rates of change. So this price of $25, you're not going to plug into the derivative. You're actually going to plug it into the original problem. So S would actually equal 0.007 times 25 cubed minus 0.5 times 25 squared plus 150 times 25. Once again, a lot of number crunching in these last couple sections, but we can do it. So that plus 150 times 25. We get, let's see, a supply of 3,546.875. So this is how many units producers will want to supply if you charge $25 per unit. Once again, I did not plug this into the derivative because it didn't say anything about rates of change. All right, now we got to do rates of change. So part C says find the rate of change at P equals 25 and interpret this result. So I'm going to need to write down what my DSDP formula was from part A. So that was 0.021 P squared minus P plus 150. Hopefully you already have that written down in your notes. So find the rate of change. So now we're going to plug the 25 into our derivative because it mentions the word rate of change. So this would be 0.021 times 25 squared minus 25 plus 150. So this would give me 100. So this is in rate of change. This would be 138.125. And it says interpret this result. So if I were interpreting this result, this would be the approximate unit increase. And I say increase because it's a positive number. It's the approximate unit increase of increasing your price to the next number up, which would be $26. So according to this information, if you were to raise your price to $26, the amount of units would actually increase by about 138. Now that's a little bit weird because that's where part D comes into play. Would you expect DSDP to be positive or negative, and why? I actually did not expect to get this kind of number, and that's a little bit weird because anytime you increase price of something, usually the supply goes down because you're having to charge more. So you would expect this to be a negative number. You would expect your approximate units to decrease when you increase price. So why? Like I just said, if price goes up, normally units go down. This is a little bit weird to see price go up and your units to also go up. That could be for a number of different reasons, such as it's really, really demanding, whatever you're trying to sell. But on the everyday item, that's usually not going to happen. All right, getting towards the end of this video, I've got a couple more problems to do. Let's do one with average cost. We haven't done that in a little bit. So number 4. The average cost for Turtlehead Incorporated to produce X units of its thermal outerwear is given by C bar of X equals 13X plus 100 over X. Use the derivative of C bar of X to estimate the change in average cost as production goes from 100 units to 101 units. Well, just based on the instructions, the first thing I'm going to do is find the derivative of C bar. So I need to find C bar prime of X. Now, this is a fraction with X's on top and bottom, and even though we have not done this rule in a while, you're going to have to do the quotient rule to find the derivative here. So your quotient rule, remember from back in chapter 1, is G times F prime minus F times G prime divided by G squared. So if I go through and take the derivative using the quotient rule, this would be G, which is X, times the derivative of f, which is 13, minus my f function, which is 13x plus 100, times the derivative of g, which is just 1, all divided by g squared. If I multiply out what's on top, you should get a 13x. This 1 doesn't do anything, so I'm just going to distribute the negative through. So that's minus 13x minus 100 all over x squared. The 13x's cancel, which is really, really nice. And you're left with a derivative of negative 100 over x squared. Now, here's where you have to understand the idea of marginals to do this correctly. You want to estimate the change in average cost as production goes from 100 to 101. So with marginals, if you're trying to estimate that change as you go up 1, you always plug this first number in, because plugging 100 in will estimate the change as you go to 101. So I'm actually going to do C bar prime of 100, and that's going to be negative 100 divided by 100 squared. I believe I know what that is, but let's just make sure with my calculator. You get negative, and this is money, negative 1 cent. So our estimation is that the average cost of production is going to go down by 1 cent. This is a decrease as you increase to 101 units. If you think about it logically, that is a good thing to have, because if your average cost is going down by a penny, you're hopefully making more profit in the end. All right, and last but not least, one more multi-part question, but I think we can get it all on one slide this time. Number 5, an employee's monthly productivity, which is M of T, in number of units produced, is found to be a function of the number of years of employment. This formula probably looks very familiar from section 3.4 when we did absolute max and min. We're going to use it again to do a different kind of problem. So for a certain product, the productivity function is the same we saw a couple videos ago. It's M of T equals negative 2t squared plus 100t plus 180. So first thing I want to do is I want to find the productivity of an employee after 5 years, 10 years, 25 years, and 45 years. So I'm going to do this really, really quickly. You want to take all 4 of these numbers and plug them into the productivity function. So you're going to get 4 different numbers here. Let's see if we can do these all really quickly. I'm not going to write them all out this time just to save some time in this video, but I'm plugging these numbers into the original. If you need to pause the video and do it yourself and try it yourself, please do that. Because remember, I can't help you on your test days. So when I plug 5 in, I got 630 units of productivity. If I plug 10 in, I got 980 units. If I plug 25 in, I got 1,430. And finally, if I plug 45 in, you get 630. All right, so here's just some different productivity levels as you move through your years of employment. Part B says find the marginal productivity function. So that just means find the original and take the derivative of it. So I'm going to take the derivative of M of T, which would be negative 4t plus 100. That's easy enough. And then to kind of wrap up one more time what this section's all about. We're going to take those exact same 4 numbers, but this time I want you to plug all 4 of these into the derivative of your productivity function, or it's also known as your marginal productivity function. And once I find all 4 of these, we will interpret what the results are. All right, let's scoot out a little bit. So we're going to find what is M prime of 5. Once again, I'm not going to write out every little detail here, but I will plug them into there. So that's -4 times 5 plus 100, which is 80. If we do m prime of 10, so that should be 60. If I do m prime of 25, that should be 0. And finally, if I do m prime of 45, that's the one I couldn't do in my head, that is -80. So what do all of these represent? So these all represent the approximate productivity, either increase or decrease. Now it's increase for the first two. The 0 means there's no increase or decrease, and the negative means decrease, in case on the homework they make you individualize it. So it's the approximate productivity increase or decrease for working and all of them would be the 6th, 11th, 26th, and 46th year, respectfully. So according to this, according to the productivity level, going from your 5th to the 6th year, you should have a productivity increase of 80. From the 10th to the 11th, you would have a productivity increase of 60. When you go from your 25th to your 26th year, you're not going to have a productivity increase at all, probably because you're nearing retirement age. And if you work all the way to your 45th year, the approximate productivity of your 46th year would actually be -80, which means it's dropping really quick, and that's probably not something your boss is going to keep you around for. So that ends the video on section 3.6, which is marginals. Remember, this section was all about if you take the derivative and plug a number in, you are approximating the next item or next unit in line of what you're interpreting. We're not going to do section 3.7. That's a topic that we don't need for anything. So in the next video, we will move into section 3.8, which we are going to learn one last derivative technique that we need to do the final section in this class.